once we have defined equivalent voltages and currents, now we will see the scattering parameter, the second tool. We know that at ports we do power measurement, because at high frequency it is very much necessary that exactly at ports we need to define powers, because at other points the power measurement will be different. Now, for measuring, you know that a 2-port network or any n-port network, linear network, we characterize by Z matrix or Y matrix, and for finding Z matrix or Y matrix of an network, we need to terminate properly the ports and measure either voltage and current. Now, that voltage and current at high frequencies, when the mechanism is through waves, incident and reflected waves. So, basically those voltage and current is actually the total voltage, total of the incident voltage and reflected voltage. Current means total current due to the incident current wave and reflected current wave. So, and at microwave frequency, the voltages are basically measured from power, which is a fundamental quantity. We have, when we introduce the measurements, we said that power measurement is another very fundamental thing at microwave frequency. So, measuring from that power, the way equivalent voltages etc. are defined, we can find out the voltages. Now, think of that if we try to measure power for at high frequency, now power is either flowing with the incident wave or flowing with the reflected wave or flowing with the transmitted wave. And remember that superposition principle applies for voltages, it does not apply for power. That means, power, we cannot say that incident power plus reflected power is equal to the total power, that is not true. Superposition wise it is true, superposition principle is applied for voltages, but for power it is not. So, measurement of power, total power is difficult. That is why measurement of total quantities, total port quantities at microwave frequency is a difficult job. But separately we can separate out the incident wave, reflected wave, that we will see in the last part of this course, that there are devices available at microwave frequency who can separate incident and reflected or transmitted waves. That device is called directional coupler. Now, that is why total power cannot be measured for a wave, we need to measure it in terms of either incident power or reflected power or transmitted power. As voltage is measured from power, so voltage also cannot be measured as total in microwave frequency. In low frequency it can be done, but at microwave frequency there is no point talking about total voltage or total current. We will have to say what is the incident voltage, what is the reflected voltage, what is the transmitted voltage, etc. That is why when we try to characterize in microwave network, we cannot characterize it directly in terms of Z, Y, etc., Z, Y, H, A, B, C, D. We still can do indirectly, but if we want to measure these parameters, then we need to measure the separate wave quantities, and that is why there was a need to define a new two-port parameter, that is called scattering parameter. So, this scattering parameter describes the network not in terms of total voltage and current, but in terms of incident, reflected and transmitted voltage wave. That is why it solves the problem of measurement of these voltages at microwave frequency. That is why in microwave frequency this S parameter or scattering parameter is quite popular. At lower frequency you have other parameters Z, Y for active devices like transistors, H or G for cascading of networks ABCD, those are popular. Now, like other Z, Y etc., this S parameter also completely characterizes a microwave network, and there is an instrument available which is based on the component directional coupler, that is called network analyzer, that can separate and measure incident, reflected and transmitted voltage waves. We will see in one of the lectures in this week this network analyzer instrument. Also this S parameter is, we can relate mathematically this S parameter with the existing Z, Y, H, ABCD etc. parameters. So, we can interchange and ultimately we can characterize a microwave network in terms of Z parameters also, ABCD parameters also etc. Then what is the need of S parameter? That for measurement, this is the way that if you have a microwave network, you either measure or estimate the S parameter, convert S parameter to other two-port parameters. So, any of them can be used. That is the popularity of S parameter, which we are calling the second tool of a microwave engineer. So, let us see, suppose we have a general N port network, and in this is an N port network, you see one port number 1, 2, 3, 4, small nth port, capital Nth port. So, we are calling that it has total capital N number of port. This is the last port. So, that is why N port network. Now, in the every port there is one incident wave, it can come from outside entering the port, or due to various things happening inside the network, there can be a reflected wave, reflected voltage wave V1 minus. Minus stands for reflected, plus stands for incident. So, you see that you have V2 plus which is coming inside, which is going inside the port 2, V2 minus going out, V3 plus, V3 minus, like that. So, we can represent, since it is a linear network. So, what is V1 minus, what is getting reflected? Suppose this V1 plus is coming, now due to the impedance level seeing here, some of this may directly come back. Also, whatever V2 plus is coming here, some of that can come here. So, that can also contribute to V1 minus, something happening in port 3, and if that power comes here. So, that is why Vn minus can be written as a linear combination of all other port incident voltage waves. If I expand this, it becomes V1 minus is equal to S11 V1 plus, plus S12 V2 plus, plus S13 V3 plus, plus S1n Vn plus, etc. So, any reflected wave at one port can be written as linear combinations of incident voltages at all other ports. So, you can write it as the various port reflected voltages, this vector is equal to this matrix, square matrix, n by n matrix, and then you have another n length, capital N length vector. So, this matrix is called S matrix. So, the same thing in the matrix form we can write V minus is equal to S V plus. This S matrix is called scattering matrix. Okay. So, now if I want to determine, so how many S parameters are there in an n-port network? There are n by n, that means n square number of S parameters. If I want to determine any of them, let us say Sij I want to determine. So, you see that Sij will be equal to, when we wrote that, suppose I want to determine S12. So, S12 how can I determine? V1 minus by V2 plus, if I put all others V1 plus, V3 plus, V4 plus, all others 0. That means, only one is exciting, another I am collecting at the reflection. So, that is why when we say Sij, that means that I have given the excitation at jth port, the second subscript, I am collecting the reflection at ith port, except jth port, all other ports the excitation is put off. How I can put the incident voltage at other ports put off? That is called match terminate. If I match terminate a port, so it cannot give rise to any incident wave. So, drive port J, when I am trying to find Sij, drive port J with Vj plus incident port. Do not match terminate this port, because if you do that you cannot give this Vj plus. Match terminate all other ports. Match terminating means, that means all other ports Vk plus the incident voltage becomes 0, and measure the reflected wave at port I. So, by this we can find out the any S parameter. So, this is the measurement thing, we put match termination at all other ports except the incident port where we are trying to give incident, and measure the reflected port as the designated port. Now, whatever we have told, that why we use S parameter, again I am summarizing that there are H, Y, Z parameters. Sorry, this H is generally small h, the hybrid parameters. So, hard to measure total voltage and current at device ports at high frequencies. I described the reason why it is so. And active devices may oscillate or self destruct with shorts or open, because in case of the other H, Y, Z parameters, that means total voltage or current measurement type of things, either we open or short a port, but that for active devices at high frequency it may oscillate. So, that shorting or opening may become dangerous for the devices at, actually that was one of the reason why transistor was defined not with YZ parameters, with hybrid parameters. Now, S parameters, they relate to familiar measurements like gain. Gain means how much voltage gain, power gain, etc. Loss, reflection coefficient, how much reflection taking place. From S parameter we can easily find those things. Relatively easy to measure, can cascade S parameters of multiple devices to predict system performance. Also analytically it is convenient. There are various CAD programs by which you can find out what are those reflection coefficients, transmission coefficients, etc. Also we will see flow graph analysis, the third tool by which also you can find out. Then as I said, there are interrelations between these parameters. So, if required to calculate H parameter, Y parameter, Z parameter or ABCD parameter, that can be done from S parameters if desired. So, you see that some incident wave A1 is put, some of that gets reflected, that we measure as S11 by putting match termination here. Similarly, we measure B1 and find this ratio. Whatever we have said already is written here for 2 ports. Now, measuring S parameter means now boil down to 2 port. So, S11 means what? That second port you match terminate and find this ratio B1 by A1, or in our terminology V1 minus by V1 plus. Similarly, S21 means you match terminate port 2 and find out V2 minus by V1 plus. Similarly, if you excite the second port and match terminate the first port, you get the other two, S22 and S12. So, that thing is described here, that you have a 2 port network we call device under test, DUT. So, in one case we put that A2 is equal to 0, that means match terminate this, find out these quantities, then you reverse the thing, put the excitation in second port, put the match load here and then find out. So, you can measure S parameter. Now, this is the device network analyzer that can measure the S parameters. So, in a 2 port network, these are available in 2 port, 4 port, etc. Obviously, 4 port is quite costly. Network analyzer is a quite costly equipment, but nowadays its price is coming down. In 80s it was invented, and nowadays in your lab you can hopefully see a network analyzer. This is a modern network analyzer, looks like this. You have a large display section, then you see the ports. It has 2 ports, this is one port, this is another port. With these 2 ports you can connect your things. Now, there is a numeric keypad here, then there is one knob which can change analog way of changing the values, and there are various buttons. By pressing buttons you can have this. So, this is a network analyzer, you can connect with this. This is one port, this is another port. With this you can connect your devices. Now, this is a closer view of network analyzer. There you will see that I think there are some frequencies you can change, then there are ports, there are stimulus, etc. We will discuss those things at a later when we will concentrate on this thing. You can put some markers. So, you see that there are one measurement function. So, various measurements, S11 measurement, S21 measurement, that you can put there. Then there is a format. Now, format means in which way you want to get the display. So, whether you want the plot as Smith chart plot, as a polar plot, as a rectangular plot, that you can do it here. Which scale you want to use, what scale, whether you want log scale, dB scale, etc. Which type of display, as I said. Then averaging, whether you want averaging. There is averaging means, suppose when you do any measurement and in presence of noise, now if you repeat that measurement, same quantity you measure several times, some measurement and take average of that, your SNR will improve. averaging improves SNR. Why? Because signal is a deterministic thing. So, if you repeat several times the same measurement, so suppose some signal value is 5 volt. So, I am taking 5 volt several times. So, then when we average, more or less I will get the same thing. But noise, it is random. So, if I take large number of noise values, their average will be equal to the mean of the noise. Generally, our white Gaussian noise, they have a 0 mean. So, noise will become reduced by averaging. That is why network analyzer, they provide various averaging things. Typically, the same measurement is done 1024 times, 1024. That improves the measurement accuracy. Then network analyzer need a calibration. We will see when seeing that if we do calibrate various types of systematic errors which occurs in a measurement, that gets reduced. Then there are stimulus that start, as we say that you can in network analyzer you can see from, you want to see the behavior of a network with by changing frequency response of behavior. So, you can select the start and stop, so that you can get frequency. Similarly, you can sweep means that frequency thing you can vary, then you can give trigger. This is like other that some event will occur, then that time I want to measure, that is called trigger. Then you can put markers, so that exact measurement values automatically will come, those are called markers. Then the instrument measurement setup that you can store, that is called instrument state, and then you can get preset, some factory level setting you can do. Then there is another one is the macro break. Yes, and this is navigation, means you can change various values. You can see any other thing. So, you can, this is a save recall button. So, that means any time you can recall any previous measurement, etc. So, this is about network analyzer. Now, this is in the microwave things, you see this an inductor. An inductor is formed by, in any rectangular waveguide, if you have a diaphragm, that means these portions are metal. So, actually the whole thing was open, but if you block some portion of it like this, it gives you an inductor. This is called a diaphragm, inductive diaphragm. This you see the blocking is in the horizontal strips. In this case, this was vertical strips. So, this is called capacitive diaphragm. That is why a capacitor is can be implemented by waveguide like this. This is a LC circuit by some rectangle. Then step, E plane step, that means the in the vertical side of the waveguide you are having a step discontinuity, that is again a capacitance. So, capacitance you can give either by a diaphragm or by a step. Similarly, H plane step, here the dimension is changing of the guide, that is like an inductance. So, inductance you can give either by an H plane step or by a inductive diaphragm. Now, these things I am showing because these are discontinuities, and there we said various higher order modes will come, that what we have seen. But net effect of them is producing an LC. In high frequency we cannot fabricate LC, but this is the way we fabricate LC at high frequencies, and you can measure that their S parameters by network analyzer. So, to give you an idea that at microwave frequencies, these are equivalent of the lump things, that here we do not use lumped elements, but these are distributed elements. The same thing that was waveguide, this is on microstrip technology. Microstrip means there is a substrate, over that there is a metallization. So, that microstrip discontinuities, the same C, then LC you can make like this. So, if you have a single microstrip, actually in a normal microstrip line this whole thing should come total, but here we are keeping a gap that is giving rise to a C. Now, two things there in between a gap. So, that gives rise to a pi C network, pi capacitive network. Then if you are constricting this transmission line, the metallization, that gives rise to a T network with two series L arms and one C. Similarly, a T here, that gives you two branch couplers. Similarly, a coax to microstrip line, that will give you an LC. So, these are the discontinuities, discontinuation, microstrip discontinuity, that equivalently can be modeled. Now, through S parameter you can model this, there are ways by which theoretically you can find, also you can measure it through that network analyzer, the result will become something like this. I am showing because in impedance measurement you can use this as your various loads. So, if you want to give a capacitor as a load, you can give either this microstrip or a capacitive diaphragm. We do that in the lab, we ask the student give that inductive diaphragm and ask him to find out what is the load, etc. So, with measurement he can do that. So, with this, in the second tool, that scattering parameter, in the next lecture we will try to find out what are the properties of the scattering parameter for various microwave networks.